All right, we can go ahead and get started. I think we'll try to get folks in the waiting room in as quickly as possible. But to respect everybody's time, we might as well just dive right in. So for those of you who don't know me, my name is Matthew Van Sweden. And I'm co-chair of the local AIA Grand Rapids Committee on the Environment, or COTE for short. Work at Foresight Management. Also with us this afternoon is Andrew Queenan, also co-chair. He works at Pure Architects. And we are joined this afternoon by Sean Costello, project coordinator at Dayton Hanneman. And he's actually going to be leading the bulk of this presentation. So we're going to deviate from how we've done this in the past a little bit. And in the past, what we've done is we've done a pretty high level overview of these different various principles within the framework for design excellence, and then invited project teams to talk about one of their projects through the lens of the appropriate principle. And that's been great and successful, but today we're actually going to just have Sean walk us through some best practices, and he's going to kind of be the on point for the whole 40 minutes. So we'll see how this goes, right? We're going to iterate a little bit here. So before we kind of get into it, I did want to take just a moment to thank our sponsors, chapter sponsors. So these folks are the reasons why we can put on this programming and share the wonderful framework for design excellence with you all. And I'm having some serious technical issues. We'll get there, I promise. So just to highlight these wonderful sponsors and thank them if you bump into them in the street, in real life, on your screens or wherever. We appreciate their contributions. I'm not an overly formal guy, but I feel like agendas set the good stage just to have expectations about what we're going to be talking about today. We're already almost all the way through the welcomes and introductions, and I'm just about to hand it over to Sean. But as I mentioned, 40 to 50 minutes, he's going to talk and share his wisdom with us. And then we're going to have some time for a Q&A afterwards. And then I'm going to leave you all hopefully with a call to action. So we have 90 minutes together. We have 83 left. So I think without any further ado, I'm just going to hand it over to Sean. So here he is, and thank you for joining us today.
All righty. Are you seeing? Oh. Don't need to see Revit. Is it still showing Revit?
I got data-driven design, evidence-based
Perfect
design.
Fantastic. Okay. So good afternoon, everybody. I'm really excited to be here. High performance design and energy sustainability, the whole gambit, are things that I'm really passionate about, things that I've had some experience in working in firms with, and I'm just really excited to share my findings with you and walk through this. So if you have any questions, please just feel free to ask or drop it in the chat. I'll try to break it intermittently and see if there's any discussions or any questions that might spark good discussions. So with that, I'm just going to jump in. So there's three main things that I'm going to be talking about today. The first group is energy and how it impacts the climate, essentially, and how energy modeling can help reduce our impact on climate change. The second bulk of things that I'm going to be talking about are best practices, load reduction, passive design strategies, and trying to figure out ways that we can redefine the existing rules of thumb when it comes to energy performance. And then the third thing I'm going to do is kind of talk about the future of energy performance and energy modeling, and talk about parametric design, which I'm also very interested in and have had a little bit of experience with, and just excited to show you guys what the capabilities of new softwares are. So I'm going to start off with this great quote from Winston Churchill. Winston Churchill stated that we shape our buildings, thereafter they shape us. And to paint the picture of where this quote comes from in history, it was right after World War II when Germany had pretty much flattened Western Europe. And Churchill and his colleagues and the government were trying to figure out ways in which to redesign and build the structures like Parliament that would embody democracy. And he knew that the way we shape our buildings shapes the environment, and thereafter they shape us. And I think this quote is really applicable to today's standards because of the issues around climate change and how buildings and the environment are now starting to affect us as humans. And we really haven't, it's a feedback loop. And we really haven't seen this like second part of the feedback loop until recently. And a great example of this and climate change is rising sea level change, which is generated by human environmental pollution, climate change, essentially. And if you haven't heard about this in New York and other coastal cities, not just New York, sea level has been rising dramatically in the last 15 years. In New York specifically, it's risen about 9 inches in the last 50 years. And this is having profound effects on the lower boroughs because it's changing real estate, it's changing, there's security implications, and then just general infrastructure. And it's costing a lot of money for these coastal cities. And now you may say like, well, what do coastal cities have to do with the Midwest? Well, the Midwest isn't exclusive to climate change either. This wonderful graphic done by a whole series of different studies of the Midwest shows the implications that climate change has on our climate if we continue burning fossil fuels, using fossil fuels the way that we're doing. And so if you look at a business as usual case for Michigan in the next less than 80 years, our climate is going to be something similar to that of northern Texas. And this is pretty dramatic because if you think about Michigan and its existing climate as we are now, we're predominantly a heating dominated climate. And if we switch and dramatically shift our climate to something that's cooling, all the existing buildings, the way that we design our buildings is going to change very rapidly. And we're going to be switching to, especially in residential, a electric-based system for cooling. And so this can dramatically affect the way energy is used in the Midwest. And a lot of the times we talk about climate change as if it's something in the future. But unfortunately, climate change is already here and it's already had the effect on, specifically Western Michigan. If you look at the last 100 years of high temperatures for the 12 months, 7 of the 12 months, the high temperature record has been set in the last decade, which when I found this data, I was pretty taken back because I don't think this is definitely something that's caused by climate change. And I think that one of the main issues that we have to think about, especially as a profession, but also in general, is where does our energy come from? We have to understand what the loop is, where it comes from. And a lot of times we don't, think about, when we turn on the light switch, where is that energy being generated? How is it being generated? And this is important because our energy grid is in most cases is not extremely effective because it's burning fossil fuels. And so if you look at this map of the United States, this is a great map that illustrates the ratio of pounds of CO2 per kilowatt. And you have Wyoming over there on the west side of the United States that's probably one of the worst or dirtiest grids. And then on the opposite end, you have Vermont, one of the more cleaner grids, well, the cleanest grid. And that's because it uses a lot of hydrological electricity with its dams. So they're capitalizing on some of the natural features that Vermont has to offer. And Michigan's right around in the middle. We're in the top half. But if you look closer at Michigan, the most amount of the consumption that comes from the consumption for the energy in Michigan is predominantly residential and commercial. It makes up almost half of energy consumption in Michigan. And this is important because those consumptions are typically from dirty sources or fossil fuel sources. If you look at Michigan and its energy sources and the consumption per energy source, natural gas, nuclear power, and coal, and some ethanol is the predominant use or source for creating energy. And if we look more specifically at electricity, a lot of that really does also come from fossil fuels, nuclear, of course, being a little bit cleaner fossil fuel, but a fossil fuel nonetheless. So as a profession, we really need to understand and face this challenge and look at what the opportunities are to reduce our energy consumption. And if we were by chance just to, align with the 2030 palette, we could cut about 30% across the board in energy use for fossil fuels, which would be awesome. And I don't know if anybody else has seen these effects recently, but consumers is actually starting to charge more for those peak times during the day. And that's because they don't want to have to build new power plants to serve the peak load during those hours. So we really do need to, think about how we can face these challenges and reduce our consumption. And in our profession, how we face these challenges are really, I think, in two ways. One is data deficiency, looking at how we can use data to not operate in a data deficiency, but use data to leverage better design decisions. The other thought is how is trying to understand the dichotomy between technology and design. Technology being, more efficient or effective mechanical systems or lighting systems, or even R value. And if we look at data, data within our profession is highly quantifiable. There are a lot of things that we can quantify in our profession. However, for some reason, energy and high performance design is something that we don't typically try to quantify, which is something that we need to start looking at so that we can make better informed decisions. So we can quantify data. If we can quantify data, we can make more informed decisions. And again, I'll talk about technology versus design. I think if we're looking at the technology within a building, we can't really rely on the innovations of technology to fix the issues of energy consumption. We really need to rely on better design. I think we all on this call can agree that adding more insulation or more effective lighting solutions or more efficient mechanical systems will definitely drop our overall energy performance. But if we can design things, if we can look at orientation, if we can look at the geometry and try to find solutions that are passive, we're not only making a more effective design, but in the end, we're not adding cost to the project. We're driving down costs because we're using design as opposed to expensive technologies. And so if we talk about design, energy modeling really, if we're talking about design and passive design, energy modeling is really important and crucial to this. And energy modeling can have a whole breadth and umbrella of things incorporated with it, including climate data, looking at climate data, looking at solar analysis, doing R-value calculations. But it's really important to look at how the process of energy modeling is handled throughout the project. This is a process timeline of a project produced by ASHRAE 209, which is, I think, the most current the newest energy standard for ASHRAE. And they're going to be stipulating that we need to do energy models throughout the course of the project to try to reduce overall energy consumption. And so if we can do energy models through the course of the project, use that data to leverage better design decisions, then we'll have a more effective project. So before I jump into load reductions and best practices and all that good stuff, are there any questions? I didn't look at the chat. All good? Cool. Okay. So load reduction. Load reduction and passive strategies essentially go hand in hand. And to understand what ways we can reduce the load on buildings, we need to understand what the load is. And so if we look at a typical project, especially in the Midwest climate, the largest piece or the largest amount of load put on a building is from space conditioning. And that's heating, that's cooling, that's ventilation. The next highest load is typically lighting. And then after that, you have miscellaneous electrical loads. And that's typically equipment and plug loads, things of that nature. And so if space conditioning is the largest load on a project, we need to understand what that load is and then try to define and quantify how we can reduce that overall energy use. And the three biggest loads typically that impact space conditioning are solar radiation, so how the geometry and the building interact with the sun through the envelope and also through glazing. The second is conduction and infiltration. So conduction being the delta T, or the difference in the ambient air from the interior to the exterior, and then infiltration, which is the differential in pressure between the exterior and the interior. The last one is internal loads. Internal loads are typically driven by people, equipment, lighting, and other things that generate heat within the interior of the space. And so if we know that these are the three largest things that affect space conditioning, we can start to develop strategies that reduce these loads and even maybe potentially optimize them to act as heating or cooling elements within the space. And so the first place we really want to start is with the climate data. Looking at the climate data is really important, and there's this fantastic software called Climate Consultant. And Climate Consultant will take the psychometric chart for, will plot the psychometrics for any specific area in the United States. And so this one is specifically looking at Grand Rapids. And what it will do is identify passive design strategies that can help reduce space conditioning. And essentially what it'll do is you can see on the top left there are a whole litany of different passive design elements. And it's prioritized those elements based upon how many hours out of the entire year you can capitalize on those passive design strategies to reduce your overall energy load. And this is something to reduce space conditioning like we had talked about earlier. So what looking at the climate data does is help define passive design strategies. And those passive design strategies that are for Grand Rapids are inherent to all projects. So the six that impacted over the space conditioning the most that could be beneficial to the project were building orientation, right sizing the building, internal heat gain, passive ventilation, south-facing glazing, and shading. And I'm going to go through each one of these and kind of talk about the impacts they have to the energy use within the project. I created a actual energy model for a 22,000 square foot office. And I'm going to walk through each one of these passive strategies and talk about how they impact the overall energy use and how we could potentially use these in everyday design. So the first one up is optimizing solar gain. And optimizing solar gain really talks about the relationship between the geometry and the sun. And I find this to be an excellent tool for, it's essentially a litmus test for your geometry. And so I ran two different pieces of geometry. They're actually very similar, except one is rotated. So the top piece of geometry has an east-west axis, and the bottom piece of geometry has a north-south axis. And this talks about why orientation is so important. If you look at the energy or the solar radiation that the east-west versus north-south piece of geometry has, you can see that during the summer, the geometry that's oriented north-south experiences a lot more solar radiation during the summer, during those hot months. Whereas during the winter, the east-west geometry actually experiences more solar radiation. And this is good because we want our geometry to have more solar radiation during the cooler months during winter and less solar radiation during the summer. And so this is exactly why orientation is so important. And this costs the owner essentially no money. It's just rotating the building. And so if we expand this graphic to other more complicated or different shapes, we can start to look at how solar radiation impacts all these different geometries. If we look at an L-shaped building, it's going to have more, not necessarily more surface area, but more surface area that's facing different east-west and southern positions with the sun. And that's why it's experiencing more solar radiation. It has the same amount of surface area as all these other concepts. And we have the north-south axis that's a little bit better than the L-shaped building. Then we come down to a square building, which is a little bit better than a north-south rectangular building. And then we have our east-west building that is performing very well. What I found to be very interesting is actually a circular building has a pretty decent energy profile or solar radiation profile. Now, typically, we don't build circular buildings just because of cost, but there could be something that you could a type of geometry that you could use that's similar to a circle that can reduce your solar radiation. And so one of the other things that we also want to look at with solar radiation is glazing ratios. And this graph illustrates, it's the same 2,200 square foot code minimum basic office. It illustrates 4 different east-west glazing ratios. And then we varied the southern glazing. And, by doing this, you can see the shaded bar at the top is showing overall energy usage. And then the deep green bar is actually illustrating daylight factor. And daylight factor, the higher the daylight factor, typically the better. And what this illustrates is there's pretty much a direct link between lighting or daylighting and energy performance. You can see that down at 5% solar glazing and 10% Western solar glazing, this is probably one of the best performing options, but it has less daylighting just because we reduced the amount of exterior glazing. When we start to add glazing, maybe to the southern enclosure, let's say like around 20%, our daylighting factor goes up dramatically, but also our energy performance does go up, not as drastically. So this could be potentially a very good option. Now, if you needed something that had a lot of daylighting and you're up here at this really energy intensive option, you would probably want to look at a glass that is not code. And so you want to look at a glass that has a higher solar heat gain value with that also high visible light transmittance for that particular option to drive down your overall energy use, your EUI. The next passive strategy that we can look at in best practice is passive ventilation. And I know this is a difficult thing to do, especially in the Midwest and with different building typologies, because typically we don't allocate controls for passive ventilation in buildings because it's expensive and it's also difficult to have that interface with the users. But there's a huge opportunity here to really drive down our EUI using passive ventilation. This same energy model, 2,200 square foot office with code minimum enclosure, if we were to add passive ventilation, we could reduce our overall use by about 27%. And this is pretty much the same across every single building typology. Obviously, there's some more drastic reductions with passive ventilation when you get into primary schools because there's a lot of internal heat gain, which I'll talk about in a second. Heat gain is another, low thermal mass heat gain is another best practice and design strategy that you can definitely have in the Midwest. If you have a really intensive internal heat gain, like a assembly space or a restaurant, or even a shopping center where there's a lot of people, there's a lot of equipment, there's a lot of lighting, electrical, artificial lighting, it's a good idea to have materials inside the space that can absorb some of that heat. And what that does is it really helps minimize peak heating loads during the day and normalize the ambient temperature inside. If you don't have these, you might start to see drastic swings in ambient temperature inside because you're having, large amounts of people or large amounts of equipment that are turned on that are giving off a lot of heat during the day, and then they're all gone during the night. And because of that, the building is experiencing these large swings. So it's a good idea if you're working with a project that has a high internal heat load, like a restaurant or a even like a data center, which isn't on here, or something that has a lot of like a conference center. It's a good idea to have low thermal mass inside the building to help mitigate those large swings in temperature. Another thing to look at with internal heat gain and minimizing your energy load is daylighting. Daylighting can be a really great strategy to reducing internal heat gain. And this is a fantastic graphic from MEAB that illustrates how having a really bad daylight or a poor daylight factor within the space can drive up internal heat gain and usage because of artificial lighting that has to compensate for the lack of daylighting. And so if you look at a hospital or even apartments, the difference between a daylight factor of 1 and a daylight factor of 4 almost, well, it almost triples if you're having less daylighting. So something to be aware of, daylighting isn't just for human health, but it's also to help minimize artificial lighting within the space. The next item to talk about are passive design strategies, right sizing the building. And I love this graphic. This actually comes directly from Climate Consultant. And I think it's so funny that a software has this baked into it, but it's very much right. It's how can we work with the client to right size the building so that it's not too drastically large. We're not having heat and cool spaces that are so big and overwhelming that they're not so big and overwhelming that that it's causing large consumptions of energy, essentially. And not only should we look at right sizing the building, but we should also look at how the building's laid out. The corner office, the old idea of the corner office, is actually really difficult to heat and cool because you're taking a sector of the building that has a large amount of exterior surface area that is experiencing the external loads much differently than the open office is. And because of that, the corner office could be in a cooling mode, whereas the open office could be in a heating mode. And having those different zones and temperatures is fine, but if we can think about how the space is experiencing those loads and have interior conference rooms or conference rooms that aren't taking up corners or offices that are on the southern side or even the north side, we can start to generate floor plans that are not just about function and where we can fit in people, but we can also start to think about thermal comfort and energy performance down to the floor plan. And then finally, the last passive strategy that I'll share with you guys is shading. And shading is really important, especially in Midwestern climate. If you look here, the Climate Consultant actually illustrates the two azimuth angles for June and December. And these are kind of like your design. You know how mechanical designers have design degree days? This is essentially the design day for passive shading. And so whenever you're doing passive shading, you want to draw those angles into the building to see how much it's actually shading, not only from a daylighting perspective, but also from a load reduction perspective. And so I ran that same energy model and varied the exterior shading. And what we found is a pretty direct relationship for the amount of glazing and how far out the south-facing horizontal shading actually comes. When we go from half a foot, 6 inches, to 2.5 feet on a 20% glazing, for south-facing enclosure, it drops about, looks like about a kBTU and a half, which can have some large implications on a much larger building. So this is a fantastic piece to look at. And, you know, this is a great example, but if you're doing a project that fits outside of these lines, it's a good idea to do energy modeling as well, again, to look at what you actually need for your energy model. But this gives you a much better rule of thumb as to how far out your south-facing glazing should go. Another thing that I really want to talk about is east-west glazing. I see this a lot, and east-west glazing and its shading is typically, I see it with horizontals. And typically, east-west shading is more effective if it's vertical. So the horizontal or the shaded bars here illustrate the horizontal shading on the east-west enclosures versus vertical shading on the east-west enclosures. And you can see it's not a crazy difference, but it is more effective. And that's a simple thing that you can just switch and it'll save you a kBTU or potentially even more just by using vertical shading versus horizontal shading on your east-west enclosures. All righty, so we're about to jump into parametric design. I think I have about 10 minutes left. I wanted to see if anybody had any questions. Okay, fantastic. Well, the last part of this presentation is to talk about parametric design modeling and how it can impact energy performance. There is a great opportunity here to use parametric modeling to iterate how our buildings are performing. And what parametric design modeling does is it allows you to take a whole litany of building inputs. So for instance, the building geometry, the orientation, the width, the height, U values, temperature set points, lighting efficiency, and it even you can even add renewables. And you can take all of these inputs and do a parametric analysis. And the parametric analysis will run all of these inputs. So we have these 20, I think there's like 25 inputs. It'd run about 15,000 simulations. And there's no way we could do that without software. So this is a great software that can help figure out what the best and most optimized solution is. And this is a typical parametric study, what you would see. There's building inputs like the length, width, height, glazing ratios, shading depth, and it gives you a bunch of building options and things that you can find that are most effective for your project. And this is something that you can do up front or throughout the length of the project that really helps you optimize the geometry, optimize the building inputs, and creates a very integrated design strategy as you go through the course of the project, because you're able to look at the very detailed and the very big concept pieces of the building. You're able to generate those studies that look at the whole piece. And so this is a Design Explorer is one tool that we use that allows you to, that has a great interface to look at a large amount of data. This was a energy simulation that we ran that had about, I think, 900 plus energy simulations. And what we were doing is able to interact with the client. We were showing the client this and pick the options that best suit them. And it's all talking about energy performance. Now, we didn't pick the lowest option because it just wasn't effective for the client, but we picked the one that had the best daylighting or was the correct width or had the proper amount of shading depth. So it's a really fantastic tool and way to look at large quantities of data. And there's other softwares that also do this as well. The Cove tool does some parametric analysis. I think Sapphira does as well. So there's a lot of tools that can do this, but the parametric analysis is really what's fantastic. This was another parametric study that we did for a competition in New York, and we were looking at solar radiation and trying to figure out what the best piece of geometry was on the site, what the best piece of geometry was on the site. And we were looking at data from the solar radiation study and being able to iterate orientation, width, the type of geometry. And so it was a very fun study. And the building that we ended up generating had, I think, an EUI of 13. So it's definitely helpful to have this at the beginning of the project. You can also optimize daylighting. This is a great tool as well because you can look at different glazing ratios and then compare it or overlay it with overall energy use, which is a fantastic tool. I think the best capability, though, for parametric analysis is being able to iterate the geometry. That having geometry that can change in size, that can change with the amount of apertures, that can be rotated very quickly is probably the best capability of parametric design, because that's not something that a typical architect has time for or even capabilities. So having a software that can do it all in one is just fantastic. And this is what is being illustrated. A office building that we decided, okay, we want to create maybe a circular shape, but we don't know if it really does need to be circle, or there's certain optimizations that we can have by changing the floor plate. And then I'll finish talking about parametric analysis with this great study that we did on an actual project. And we were talking to the client. The client wanted to attach this new building to an existing building. And as we were starting to do the energy analysis, we noticed, this wasn't going to work because it's a north-south rectangular building as opposed to an east-west building. And so we were already starting off on the wrong foot. So we said, okay, hold on. We're going to do this energy analysis and we're going to see if it's actually better to have it rotated or at a 45 degree. And that's what we did. And we looked at glazing ratios. We looked at the width of the building, how tall it should be. And we came up with a very good solution that ended up changing the course of the project and becoming a whole separate project that was not going to be attached to the existing building. So there's so many possibilities, so many opportunities. Parametric design and parametric analysis are a great way to do energy modeling. And so I'll just loop back and just talk about real briefly again that we need to face the challenges of how humans shape buildings, because the buildings will shape our environments and they will eventually shape us. And we need to understand what this feedback loop is. And there's a great opportunity to reduce our consumption and create high performance design. And one of the ways we can do that is using data to leverage good design decisions so that we can make informed design decisions that are more effective and more efficient for our clients. And I'll just end with a 2030 plug, which I know Matt's going to talk about in a second. And 2030 is a great way to benchmark and have a goal for what your overall energy use is. If you haven't looked at 2030, I definitely encourage you to look at the Zero tool. It'll help benchmark your building and have a goal for what your project should be. Not just be the best, but have a goal that you can design towards and running your energy modeling and iterations on. So anyways, I hope this was really helpful. I hope this changes some of your rules of thumb and looks at data and architecture and energy modeling in a whole different way. If you have any questions, please let me know. I'm happy to talk about energy modeling and any questions you might have. So thank you very much.
Thanks, Sean. It's a great segue into the question and answer session, right? So, I know there wasn't a whole lot of questions in the midst of your presentation, but I am kind of curious if anybody has any questions now, because this is really the point of this latter part of this event, or this programming. So, anybody have any questions for Sean? Anybody have any questions for anybody on the call about designing for energy modeling, the iterative design process? Yeah, I have a few that I could throw out, but I wanted to create a moment for anybody to ask one on their own volition. All right, well, I guess my question, and it's kind of for both you and Andrew, because I know you guys both kind of wrestle with this in a similar capacity. I'm curious, the evidence is pretty clear, right? Like, we can achieve higher performing buildings without adding a whole lot of cost if we just do some of this analysis at the most ideal part of the design process. Why aren't more folks doing it? That's my question. If it's such an obvious choice, right? Like, why aren't more people doing it?
I'll chime in here. I think sometimes there's maybe like a hesitation, like it feels the whole energy modeling, trying to predict what the future outcomes are going to be, is an overwhelming and difficult process to overcome. And so I think that sometimes feels too daunting for people, and it isn't necessarily something that's taught in like mainstream education in a college arena. So I think that has a piece of it for sure.
So you think it's a training, like we're not formally taught how to do this, and so we're not very confident in, or maybe we're just overwhelmed by the prospect of trying to learn something.
Yeah, I think people are just a little overwhelmed. They hear energy modeling and they kind of balk at it, which is understandable. It's yeah, it's a very daunting thing to try to do. You're essentially trying to predict the future, and
No big deal.
so it's a difficult thing to do.
I think too, as some of the tools have come a long way though, where they've gotten simpler. I feel like I'm one of the rare people that came out of LTU that hasn't used Grasshopper and Rhino, but I know a lot of people use it to do energy modeling. But I think things like Cove Tool have tried to make it easier at the beginning. And so I think my answer to the question that is a bit different is that I think sometimes people lack the commitment. Far too often, it's in some, just as we've been doing this over the last year, I hear comments around it's another thing, or
more time,
whatever. And to me, I'm like, you got to design the wall section, right?
Yeah.
So like start there. Like it doesn't matter if you use new approaches to insulation or not. You have to do the wall section. So do the wall section better. And I think maybe it sounds harsher than I mean it to, partly because I think people I've seen standard details that have clearly been around for 10 or 15 years that have continuous insulation. So at some point, someone took the initiative and said, we should be doing this, and it took over. And I think that the same is hopefully going to be true of energy modeling, where I think people are, hey, I can get Cove Tool and do some quick early studies and look smarter in front of an engineer. Great. All right, I'll do that. So.
Well, and to that point too, passive design strategies have been around forever as well. Joe Stiebrick has this great slide where he looks at like traditional architecture versus modern architecture, and the R value of traditional architecture is much better than, you know, Louis Sullivan's skyscraper tower. And it's just it's how we allocate materials, it's design, it's it's not rocket science. We just need to do it, you know.
So my second question, and I'm going to keep asking questions until somebody else does, is kind of aligned with the first one. But, you know, you had mentioned in your presentation that you kind of pulled up like this tool live in front of a client, you know, and started doing some of this analysis.
Yeah.
My question is, how long did it take you to get the confidence in the tool and your ability to use the tool to actually pull it up live in a client meeting? Because that seems a little like daunting, if I'm not going to lie, right? Because that could go a whole lot of ways,
Right.
multiple scenarios, but going sideways, right? So maybe just share a little bit about that particular experience.
Yeah, sure. Well, so parametric analysis has its own piece, and actually how I gained a lot of experience with that is actually immersing myself in competitions. So I've done a few competitions where I was able to test my assumptions, test the software, and be able to present it, which was like it was a very good practice to go talk to clients about this. So I kind of had the practice beforehand, which was really nice. But I mean, it's really, for me, I'm very passionate about this. I think this is a great opportunity that's missed in a lot of firms that you can capitalize on, especially if you're a young emerging professional. If you can, you know, hop onto this energy modeling train, it really opens up avenues for you, and you can take that passion and, you know, eventually talk to clients about it, and they understand that you're energized about it and you're happy about it, and so they understand that you do have the confidence in it.
Yeah, that's great. I think I've long been a proponent of design competitions, not to solicit, you know, who to do work like, 'cause I think that's a little bit exploitative, but like the act of just engaging in you know, these hypothetical problems to solve and getting you know, emerging professionals or junior staff an opportunity to try a new skill, I think that's just tremendous. So kudos for you to take the initiative to kind of seek out those opportunities. That's great. My next question, again, nobody else is asking any other questions, so I'm just going to keep going. I've talked about like this kind of early phase modeling and kind of the iterative approach and testing passive systems and strategies. And I have to say, sometimes it has a feeling of it just it validates. I'm trying to think of how to frame this. Do you think the modeling actually changes decisions that you would make as a designer, or does it just simply validate your own intent or like intuition around what's better? You know what I mean? Like, I've gotten feedback before, like, why do I need to model this? I know this way is better.
Yeah.
You know, why do I need to do this extra work? I already know, right?
Yeah.
And maybe unpack that a little bit through your experience. And Andrew, you can feel free to chime into your others who've done this work. But my question is just, you know, what do you say to that kind of, and it's not a critique, but, you know, that position, that perspective?
Yeah, that's a really good question. I've been in both scenarios, and I will say, like, you have architects that like design things based upon a rule of thumbs, and they're really just using energy modeling as like a compliance tool to see if their assumptions are correct. And you that's one way to use the tool. I think the better way to use it is to use it as something to find different pathways or innovation within the project. And I will say, doing energy models is great, but you're still basing it upon your initial assumptions. At least you're changing, hopefully, through the process and like looking at the output that the energy model is creating. But I will say, like, a plug for parametric analysis is you can look at a lot of inputs in a short amount of time and be able to test so many pieces of the building very quickly, and at the beginning of a design process, where typically like you don't do the optimization or whatever till the end of the design process. So I would say like parametric design is awesome in terms of being able to have that initial energy analysis, that initial, oh wow, this is how we might be able to like save some energy by doing this because we did this study. So
Right.
I think I've probably used it in both ways you've asked it, both to validate an assumption and to convince someone. I think I've seen it a lot more with daylight analysis, usually, where I think partly because it's a little more, it's easier for an owner or a client to understand that, like, hey, you're going to have more daylight versus, hey, you're going to use less energy. And they're like, you rotated the building 5 degrees. I don't understand.
Right.
So I think, but I think both tasks are in the effort of the same thing, which is what gets you talking to an owner about that topic. So if we increase daylight, we can reduce lighting load. And from there, maybe they don't really care about energy. They do care about daylight and productivity. And so you sort of achieve ends both ways.
Right. So I have to say, and I'm sorry, Dan, I know you put your video on, so I'm sure you have something to say. But I want to say one thing. Every time I hear Andrew's kids in the background, I chuckle, and I love it because we're normalizing right now how to be both a dad and an architect. So kudos to you, Andrew. Keep it up. You're doing great work. So that's all I wanted to say. Dan, it's all you.
Yeah, before I have to take my daughter for a COVID test because we're going to a concert in 2 days. So yes, as a dad. Hey, Sean, just to, as the civil, I'm thinking about the rotation of buildings, and I'm just dreaming of the day when we get like a variance because the parcel's on a northeast, southwest, slant, but the building really wants to be square to east-west. Do you have any examples? Or the other thing I'm thinking is just, buildings closer or further apart that may affect this, to where, hey, we should push outside of the setback and put this building closer to this other building.
Hope you muted yourself.
We lost your video or your audio.
Oh, and try and go get a variance, for the setback requirement. Have you had any examples like that? Have you guys been thinking that way? That's where my mind went as you were presenting. So
that last parametric analysis that I was showing, the one where it was rotating, we pushed back, and it it was an interesting conversation because it's in a part of Kalamazoo where there's a railroad, there's a lot of electrical overhead lines. And so the initial reaction was to orient it north-south, just because that's what worked with the plan or the lot. We pushed back and we said, no, we need to rotate the building. It's better for energy performance. And it ended up sparking this whole different conversation because it's a little bit different, but the power lines ran right under where we were where we were looking to place the building, even in the north-south orientation. So it ended up being something that was really positive for the entire project, because we found something very earlier on when we were still in the SD process. So like I said, energy modeling helps with opportunities. But yeah, I mean, that was one awesome piece of it. And what we ended up doing was pulling it away from the existing building and putting it in its own parcel behind the existing building, away from the power lines. So yeah, I mean, I don't, if you believe in the data, I think it's okay to push back and say, you know, here's what you need to do. In terms of, you know, zero lot line buildings, you have to get creative. There was a building that we did down in Indianapolis that ended up becoming a horseshoe instead of just a big rectangular block, because we were trying to maximize daylighting on the south face. The first floor was still a zero lot line building, but the top offices, we could kind of iterate and change where it sat within the grid to have more effective daylighting and solar performance.
Yeah, and I'll also add to that, you know, the building context is often something that gets ignored, especially in early iterations of this modeling, because if they're not built, right, they're not typically known. But even like existing trees and their canopies, you know, sometimes those don't make their way into some of this analysis, but they actually have a pretty significant impact on, you know, the radiation kind of analysis that you were doing earlier, Sean, or talking about, and also like daylight. So I think that's where the interdisciplinary approach of like engaging, you know, civil landscape folks into the conversation to help kind of understand, like even the idea of windrows or trees to shade the building facade, or you know, where the existing adjacent buildings and what kind of shade does those cast, you know, create opportunities for more nuanced and informed solutions from an architectural perspective. So I think that's a really great question, Dan, and thank you for asking.
Yeah.
What I also find interesting about, you know, this whole, does it validate rules of thumb, you know, that you mentioned the 2030 palettes, which exist to, I mean, if we're honest, they exist to allow designers to make good choices without having to do the modeling, right? Like that's the whole point of the 2030 palettes. But I asked the question kind of in jest because I obviously have an answer, because I get asked all the damn time. But I just was in a recent project where we were doing very similar sort of integrative early phase modeling, and we were looking at all the parameters, right? And, you know, 3 or 4 different variations of every just kind of envelope attribute that you could think of. And it's kind of, and we phrase it a lot of building sensitivity analysis, right? Like what does this building, what is it sensitive to? And it identified, because it was a single story building, right? Like roof insulation had a way more impact than envelope insulation did. And the design team was like, well, we can't just add roof insulation, because I mean, that's just a lot of money. And even though it's sensitive, it means that we're still not talking about a return that's going to pay for that additional insulation. And I said, well, wait a minute. You know, the current design is also overperforming on the envelope, right? We're putting in 3 inches of rigid and continuous insulation, where, you know, we only really need 1.5 or 2. And what that analysis allowed the team to do, be like, oh, we're actually like, our bases, our like base intuition of what's best needed to be challenged, because we were overspending in wall insulation, underspending in roof insulation. And to pay for the difference, or the more impact area, is actually to, you know, potentially reduce the wall insulation to increase the roof insulation, right? So it's like that insight wouldn't have been gained if we didn't do the analysis, right? And it's not really about like proving one thing or another, but it's discovering like, oh, you know, like there are real cost implications to these decisions. And if you don't illuminate what's on the table, right, like what we're actually talking about, we can never really tailor, like really optimize the solution, right? If we talk in generalities, we're just going to get general kind of feedback, and that's usually not very helpful. Anyway, throw that out there.
It made me think of your original question when we started, and I think it's a missing piece that happens, I think, in a lot of projects. We've all been in value engineering meetings. Something's removed.
Our space.
Something's removed without understanding the impacts, and
Yeah,
it's not always energy related, but I think that's another place to me where I see the value of energy modeling is not only to demonstrate the cohesiveness of what we're thinking, but it's a little bit of justifying, because always it's, well, the architects are just spending a ton of money. And it's like, no, you have a 100,000 square foot, 1-story building. Don't put anything in the wall, put it on the roof. Oh, you have a 5,000 square foot building. That's 50 feet tall. Put it in the wall. The roof doesn't do anything for you. And like, I think it's that level of thinking that is still a little nebulous for people that aren't experienced builders. And so to have the backup of even a rough energy model is like, oh, now I get it. I see what you're saying. Great. You've made me spend the money where I should spend it to optimize the long term. And in the meantime, you've also achieved your value. Like, I've had clients too that are like, is climate change even real? And I'm like, biting my tongue. It's like, there are people out there like that, and that's okay.
Send them the map.
Yeah. There are people out there that are like that. And so it's like, all right, now I can shift it and go, well, hey, they said, take this out of your roof and put it in your walls. But actually, I ran the math. That's a bad investment.
Right.
Oh, well, thanks. That saved me money. And it's like,
yeah, I mean, that's why I love leading with values, Andrew, is because like to that point, like clients could give a shit about climate change, and you could like write them off and like, well, I'm not going to work with you then. But if you find a way to talk about the same thing with through the lens that is impactful to them, like being good stewards of your money and optimizing the dollars you're investing in this building, this infrastructure, like that means something, right? And if you can say we can get you a better performing building without spending any more of your money, like why wouldn't you? Because long term, that's saving you operational dollars, right? So that's the level of nuance I think we don't see a whole lot, but I'm excited to see more and more teams, two of you, right, doing this in your practice as a kind of standard, and certainly in my space, getting invited by other teams to kind of help them navigate some of these early design decisions has been just tremendous opportunity, because that's where the low cost is, right? Like Sean, when we're talking about this prep, right? Like the shift to go northeast, or sorry,
east, west, north, south.
Yeah. I mean, that didn't cost any more money.
Nope.
It was just a move on how we mass oriented the building on a site, right? Like, granted, it did cost money, like it actually saved money because you didn't have to move an underground buried utility, but there are some cost implications for how you site a building on a site, but generally it's like the architecture cost doesn't change.
Yeah, right. Yeah, I mean, it's hard to, back to like what you were talking about originally, doing that energy analysis early on, it's really, and having cost associated with it, it's really hard to argue against it.
All right, I'm going to call people out. They don't have to like answer, but I did want to create some space because there's three of us that have been talking an awful lot. So I'm going to call out Marie, Tong, or Michael. Do you guys have any thoughts, questions, comments? Feel free to kind of jump in, or if you're just listening in the background, that's cool too. But I did want to create a space to encourage more questions. All right, that's a resounding no. That's cool. I'm just teasing. I mean, I could honestly talk about this for a long time, but I'm also interested in giving you all 15 minutes of your days back. So I think without, unless there's any closing comments, Sean, you want to make, or Andrew, I'm gonna make my call to action. Cool. All right.
Sounds good.
So I'm gonna try to do this thing and maybe it works. So here's the call to action. I mentioned this in the honors award ceremony last week. You know, last year we introduced the Sustainability Design Award, and there was some intention and reason behind that. It was really meant to be a signal to our community that we're going to have to start paying attention to this through the lens of the honors award program. This being sustainability and performance and all the things that we need to address from a kind of built environment perspective in response to climate change. This past year, so last year we just said, hey, we'd appreciate if you talked about the framework for design excellence in your award submissions. This past year, 2021 honors award program, we actually required projects to talk to at least two prompts within the framework. They could be any prompts. They could be 2 prompts within one principle. It could be anything. We just said 2 prompts, and it was meant to like really force the teams to actually talk about their projects through the lens of the design. Sorry, I said that again. One of these days, I'll get it right. The framework for design excellence. And I mentioned in sorry, when I talked about the award this year, the program, I said next year it's likely that we're going to require some actual quantifiable metrics, and energy use intensity is one of them. So here's the real call to action. You know, next year, if you're looking at entering your project in the Sustainable Design Award category, we will, and I say likely yet because it hasn't been formally agreed upon, but it's very likely that we will be requiring you to report your energy use intensity. So that feels germane to this conversation, right? So Sean just spent a good bit of time talking about how to reduce that and improve your performance in that space. And a lot of them don't have cost, right? So it's kind of a no-brainer sort of stuff. So that's one call to action, right? Like, start thinking about this stuff now. Think about what you can do to improve your energy use intensity. And the second one is, as Sean mentioned in his last parting slide, join the 2030 commitment already. Just do it. It's really important that we do that. We have collective response to this crisis, right? And the 2030 commitment really frames up how and why architects need to be thinking more in this space. So that's it. Thanks everybody for your time. I appreciate it. It's always a pleasure spending time with you all. And we will have another COTE framework for design excellence presentations in a couple weeks. If I take a couple minutes, which I should have done before I said something, it is going to be on design for resources. So design for resources in a couple weeks, November 18th. Tune in and take care of yourself in the meantime. Thanks, everyone.
Thanks, Matt.
Thank you.